standard model field content. A second Higgs doublet that transforms as a doublet under the standard models SU2. And this is a very well-motivated model. Theoretically, it's inspired from some of the GARTs, from some of the string theories. Beyond theory, it's also a very popular model for phenomenology because it provides a very rich structure for the Higgs sector, and we can get new insights into the electroweak symmetry breaking. Also, it can help to address the hierarchy problem by taking care of the quantum corrections to the Higgs mass. Furthermore, it can also give us new sources of CP violation beyond the standard model, which is required in order to explain the observed baryon asymmetry in the universe. So that's another opportunity the two-Higgs-doublet model gives us. And it has also a rich structure in the Yukawa couplings, which lets us build more complicated flavor symmetric models. And that gives us more intricate patterns required for explaining fermion masses and mixings observed. Furthermore, it can also give us hints to new physics. For example, one of the Higgs doublet can be a dark matter candidate. It can give us viable pathways to resolve some flavor anomalies. It can help to explain build models that can explain the excess in anomalous magnetic moments, for example. So overall, this is a very well-motivated theoretical model, has very rich history of phenomenology, and overall a very attractive model. Now, what I want to talk based today is essentially looking at the cosmological aspect of one of these models and see if we can probe two-Higgs-doublet models beyond colliders. So now let's take a look at some of the known problems or issues with the two-Higgs-doublet model. So one of the known issues is the tree-level flavor-changing neutral currents. So absences are a known problem in two-Higgs-doublet models. It basically requires that all the fermions with the same quantum numbers, they must couple to the same Higgs. Now, there could be different ways to do that. One of the popular ways is the so-called type 1 two-Higgs-doublet model or the fermiophobic two-Higgs-doublet model. So what you do essentially here is you say that all the charged fermions, they must couple to the second Higgs-doublet. So you're basically separating one of the Higgs-doublets and saying that all the fermions couple only to that and not to the other one. Now, how do you ensure that it only couples to one of the Higgs-doublets? A naive approach could be by imposing an ad hoc Z2 symmetry. So for example, we can make the charge fermions odd under the Z2 symmetry and one of the Higgs doublets odd under the Z2 symmetry so that only it couples to that and not to the other one. But of course, with discrete symmetries, many problems come. So probably a more elegant approach or more satisfying, theoretically satisfying approach would be if we can embed the Z2 in a continuous gauged symmetry, for example, in a gauged U1 symmetry. Now, embedding this in a gauged U1 symmetry is essentially saying that we are extending the standard model with a second Higgs doublet and further a U1 symmetry. There could be more advantages to have a U1 symmetry in addition to the standard model gauge groups. For example, if we want to explain the light neutrino masses in the standard model, one of the popular ways is to extend the standard model with three right-handed neutrinos, and these three right-handed neutrinos via the seesaw mechanism can give mass to the standard model neutrinos. Now, if we include this extension in the type 1 two-Higgs-doublet model, then having a gauged U1 symmetry also allows us to make this model anomaly-free. And furthermore, it also helps us to explain why the right-handed neutrinos have very heavy majorana mass. One way to explain that could be that the U1 symmetry is broken at a very high scale by a complex scalar. And that complex scalar then gives heavy mass, majorana mass to the right-handed neutrinos because of the higher scale of symmetry breaking. So this idea is again very similar to what we do in the so-called Majoron model, although in the global symmetry case. But essentially then what we are trying to do here is that extending the vanilla type 1 two-Higgs-doublet model by including a U1 gauge symmetry and by including three right-handed neutrinos, and furthermore an extra complex scalar field, which would break the U1 symmetry by getting a non-zero wave. So if we look at the field content beyond the standard model fermions, we have the right-handed neutrino, we have the two Higgs doublets, and we have the complex scalar. These would be charged under the U1 symmetry that we're imposing. I'm calling this U1R because I'm assigning the charges in a way so that it can only couple to the right-hand fields. Now, one of the interesting things is that for this kind of charge assignment, which is one of the choices, not necessarily the only choice. So this particular choice ensures that flavor-changing neutral currents are prohibited at tree level and no Kähler anomaly is present. Also, it does something interesting is when this scalar field spontaneously breaks the U1, it breaks it into a Z2, intermediate Z2 symmetry. And we'll see that this is a crucial thing for the cosmology that we would study for this model. Now, after this intermediate breaking into Z2, then we have this following scalar potential for the two Higgs doublets. Now, one thing to notice here is that if we did not have the U1R symmetry, then in the most general scalar potential that we could write for a type 1 2-HTM would also include this CP violating term. But because of the particular charge assignment here in the U1 symmetry, this term would not be allowed anymore. So what we have here after the U1 symmetry breaking is a scalar potential where there is no CP violation. So we will not get into those aspects of 2-HTM where there could be CP violation, or we could do explain baryon symmetry and such things. So we'll not do that here. Okay. Now, another thing to notice is that in the scalar potential, all the parameters, if we choose them to be real, then the waves are supposed to be real. So we have two waves for the two Higgs doublets. What we require is that this relationship, that the square sum and the square root of that has to give us the observed standard model wave at 246 GeV.
So
Now,
Moinul, we have a question. In the previous slide, this U1R is global or local?
It is
The
local.
U1R symmetry, local.
Local, yes. It's local. Okay. Now,
may I ask a question?
Yes, please.
Again, in the scalar potential, so this symmetry is local, but there is this term M12 squared, which seems to violate the symmetry, no? Because the charges of the doublets are different. Or no?
So this is the potential after the U1 is broken.
After the
U1 is broken. So this would be still symmetric under the Z2.
Okay, thanks.
Sure. Okay, now we can look at different bases to analyze the scalar spectrum. For example, one of the bases is the so-called Higgs basis. So let's say we define the ratio of the two waves of the 2-HTM with the angle beta, with this tan beta relation. Then we can rotate the fields by this angle beta. Then we can say that basically one of the scalar doublets is getting a non-zero wave and the other is not. We could also look at the mass eigenstates in the mass eigenbasis. So let's say this capital H and small h, these are the mass eigenstates. So let's suppose we achieve this by rotating the fields by an angle alpha. So after this, we have these fields and we call this a mass eigenbasis. Now, interestingly, none of these two bases, the Higgs basis or the mass eigenbasis, the fields do not reproduce the observed properties of the standard model Higgs. Now, in order to do that, what we have to do is we have to rotate by a combination of these angles, beta and alpha, with the angle beta minus alpha. And in that case, this field, HSM, this reproduces the observed properties of the standard model Higgs. Now, we want to look at a particular case of this field where we are taking that the angle beta minus alpha is equal to pi by 2. In that case, this field small h, which is one of the mass eigenstates, it would coincide with the standard model or observed standard model state. So we call this the alignment limit. One of the reasons why people look at the alignment limit is that, of course, it is consistent with the experimental constraints and it's simple enough to study. So we will focus on the alignment limit. However, I'll also discuss what happens to the cosmology if we deviate a bit from the alignment later. Okay. Now, as I was mentioning before, that what happens in the scalar potential, what happens in the scalar potential is that after the U1 symmetry breaking by the complex scalar field, we are left with a residual Z2 symmetry. Now, this Z2 symmetry would be further broken when one of the scalar doublets would get a non-zero wave. When that happens, we have basically two choices. The wave could be plus V or minus V. what you say is that there are regions in the space-time which randomly pick this plus V or minus V wave, and we call these regions in the space-time or patches in the space-time as domains. Because the space-time then would be split into many different domains, they need to be separated by something, and in this case, they are separated by planar walls, what we call as domain walls. Now, in order to study the evolution of the domain walls, we can look at their field equations, this following field equation. Now, in this case, we have two scalar fields, two Higgs-doublets. So we need to basically look at a combined system of equations, because when, for example, if we look at the right-hand side, taking the derivative of the potential with respect to one of the fields, we will for sure get terms containing the other field. Whereas on the left-hand side, we have the same field. So basically, we will have a coupled system of equations, and it becomes a bit quite difficult to solve these equations numerically unless we go to some approximations. Now, of course, we have the boundary condition that at the plus infinity and minus infinity, we achieve the plus V or minus V. But in between, in the field space, the field would go from, let's say, from plus V to minus V following a certain path. And solving this equation essentially means that we are able to trace that path in field space. So a typical approach would be to split this into two parts, the parallel part and the perpendicular part. And in that case, we can split this equation into these two equations. Now, I will make a further approximation to make life easy. So in the alignment limit, we can express the two fields with a single variable. In that case, we see that without omitting the details, the correct path for going from plus V to minus V is essentially joining these 2 points with a straight line. So an advantage of doing that is that in that case, we can, by this replacement, we can basically express the previous coupled system of equations into a simplified field equation with one variable. So this equation has well-known solution in terms of tan hyperbolic functions. So we can express the field values in terms of this tan hyperbolic function. And it's also quite easy to calculate the surface energy density in the domain wall, which is given by this. So we see that in both cases, these are basically determined by the quartic coupling lambda and the scale of the symmetry breaking for the Z2 symmetry. So in this case, this is the VSM. So because we are in the alignment limit, we can say that essentially the waves are close to each other. So they would be very close to the 246 GeV. So whichever is has the largest one would break it, but we can roughly take them to be very close to each other. Now, what would be important for cosmology is this surface energy density. Then we can look at the effect on surface energy density. What happens to the surface energy density if we deviate from the alignment? Now, experimentally, we can deviate only a little bit. And if we do that, we see that after solving the system of equation numerically, there can be at max only 15% deviation in the surface energy density, which I'm showing here. So for example, let's say the alignment limit was essentially saying that this alpha minus beta plus pi by 2 is 0. Let's say it's not 0, there is some deviation from it. So if it is 0, then the blue line essentially shows how to go from minus V to plus V by following a straight line in the field space. On the other hand, if we allow some deviation, what I'm showing here is the maximum allowed deviation for positive and negative deviations. In that case, by solving this system of equations numerically, we can trace the path in the field space, slightly deviated from the straight line. And we can look at the corresponding surface energy density here. So this blue curve is the surface energy density for the perfect alignment limit. And these two lines, dashed lines, are for the deviations shown here. We see that they're still in the same order of magnitude. So, because what we would be doing roughly an order of magnitude calculation, there are many uncertainties in the theoretical calculation for gravitational waves. So for us, it really doesn't make much of a difference. So for going further, I will consider that I'm doing my calculation assuming the perfect alignment. Okay, now let's take a look at the cosmology. What happens when these fields get vacuum expectation value? So as I mentioned, that first the complex scalar field breaks the U1R symmetry to a residual Z2. So whenever a U1R symmetry is broken, a gauge symmetry, we will have a cosmic string network created from that. Now, further, when the Z2 symmetry is broken by one of the two Higgs doublets, then because it's a Z2 symmetry, we would have any kind of discrete symmetry breaking gives us domain walls. The interesting bit here is that usually you would expect that the domain walls are infinite planar walls, but here this Z2 symmetry is essentially coming from a U1 symmetry breaking. So this is an intermediate symmetry. So whenever these domain walls are being created, cosmologically, we already have cosmic strings in the universe. So these domain walls are not entirely free. They cannot simply be separated by planar domain walls. What happens is that they basically get attached to the cosmic strings. Now, to give a pictorial idea of this, suppose we have the U1 breaking and cosmic strings, which are typically horizon-sized long strings, and then they intersect with each other. So eventually we end up with something called string loops. So let's say this is one of the loop. Then here, let's say one of the fields has a phase theta, and suppose it has a U1 charge of 2, which means that theta and theta plus pi are same, because if we multiply by the charge, it would become 2 pi, and so essentially it would be the same thing. However, if instead of 2, it has a charge 1, then it would be theta plus pi, which is essentially negative of, it contributes to a negative number, this pi phase. So if we start with V, we would end up with V if the U1 charge was 2. But if the U1 charge is 1, then we start with V, but we end up with minus V once we traverse this string loop. So it means we can think of this plane of the cosmic string loop that the bottom side is like plus V, and in that case, the upper part would be like minus V. So these two domains need to be separated by something, because this will happen everywhere on this string loop. Essentially, we can say that the domain wall has to be contained within the periphery of this cosmic string. So that's the idea of having a domain wall which is bounded by the cosmic string. And this is a topological hybrid topological defect. So what happens after the creation of the hybrid defect would be the cosmological evolution would happen to both of them. It cannot happen independently to just the cosmic string or just the domain. Okay. Now, to study the evolution of this network, one of the important parameter is this parameter called RC, which is essentially the ratio of two parameters. The first parameter is mu, which is related to the tension in the cosmic string, and it's roughly given by square of the scale where the U1 symmetry is broken. And the parameter in the denominator is related to the surface energy density of the domain wall, which is again roughly related to the cube of the Z2 symmetry breaking in this case. So this parameter then essentially encapsulates what is the ratio of the two symmetry breaking scales roughly. Now, what happens after the U1 breaking is that, as usual, we would have a horizon-sized cosmic strings, and then they would intersect with each other and create loops. So up to this point, the universe has no idea whether there will be an intermediate symmetry breaking or not. So it's just like we have a typical cosmic string network, and the evolution is such. So these cosmic string networks, the loops would oscillate non-relativistically, and while doing that, they would emit energy in terms of gravitational waves. So we'd start to have gravitational wave spectrum, which typically is quite flat because they are oscillating non-relativistically. But at some point, when we have the Z2 breaking, suppose that happens at some time when at TTW, which is determined by when the Z2 symmetry breaking scale, what the Z2 symmetry breaking scale is. So when that happens, we would create domain walls, and these domain walls would get attached to the cosmic string network. Now, what's important is that it's we need to carefully look at when this happens. So if it happens too early, if the domain walls are formed too early, which would be, for example, when if V Sm or the scale of the Z2 breaking were sufficiently large. So essentially, we are talking about we have U1 breaking, and then not too late, we have the Z2 breaking, which means the two scales are close to each other. In that case, those domain walls would have to wait until they can actually impact the evolution of the cosmic string network. On the other hand, if we wait a lot. So, for example, the U1 breaks at a large scale, and then there are orders of magnitude difference between the Z2 symmetry breaking scale. So cosmologically, it happens a bit later. In that case, right after the creation of the domain walls, they would be able to impact the evolution of the cosmic string network. So exactly when this happens is given by this time t star, and roughly this is of the order of this parameter RC, which we saw that is related to the ratio of the two scales. So after that, we'll see that the domain walls would kind of put some kind of tension on the cosmic strings and make them decay earlier than anticipated. What it means is that if we have a pure cosmic string network, so they would follow a certain kind of evolution. But now, because of this emergence of the domain walls, they would put extra pressure onto the cosmic string network and make them decay early. And these would have a distinct signature on the gravitational wave. So if we want to look at now the evolution of the gravitational wave spectrum, so we can study this way. We have circular cosmic string loops, which are losing energy following this relationship. So here it's entirely determined by the parameter mu, which is essentially the scale of the U1 symmetry breaking. And then once we have cosmic string loops, which are radiating energy like this, so their radius is getting smaller and smaller. And at the same time, there are new loops being created from the horizon size strings. So it's a process where you continuously create new loops, but also you have already created loops from before, which are evolving and being shrunk and shrunk by emitting gravitational waves. So we can study their evolution from this equation. And here, as you see here, this parameter RC, which is a ratio of the two scales, it would go to infinity if there were no Z2 breaking. So if it were a pure cosmic string case. And in that case, we see that we would get rid of this term, and this would be a simpler equation for pure cosmic strings. But because of the presence of this Z2 breaking, RC would be a large, albeit it would be a finite value. So in that case, what you want to solve from this equation is to know when the new loops are being created. So it's a bit tricky numerically to do. I'll talk a bit more about that later. But this is essentially the difference, that because of the presence of the intermediate scale, you have this extra term in this equation. Now, the standard process to study the evolution of the gravitational waves is to split it into Fourier modes. And then we have to take into account the rate shifting, because the cosmic strings are created very early in the universe and they're emitting gravitational waves at that time. But what we are observing is the gravitational waves of the interferometers today. So we have to take care of that with the ratio of the scale factors. Here, T0 is the present time and T tilde is exactly when the wave was emitted. And then we can basically sum over all of these k modes. And also we have to integrate from a very early time in the universe up until today. So this integral basically encapsulates that we are basically accounting for all the loops which were being created from a very early time to today. And we are summing over all the Fourier modes. So, I mean, I will not get into the details of this, deriving this is a bit tricky, but let me point out that again, the parameter RC, it goes to infinity if we do not have any intermediate Z2 breaking scale. So if it were a pure cosmic string case, and in that case, you get rid of this term and this term here. And then this equation exactly coincides with the well-known case for pure cosmic strings. The other thing to notice here is that we have a theta function here that essentially says that we are only trying to look at those modes which were emitted after the domain wall has been created. So if you remember, T star was essentially when the domain wall starts to impact the evolution of the cosmic string network. So we are looking at loops which are created after that. And this is what the evolution of the gravitational wave spectrum looks like. So here the solid line is for the hybrid network. I'm showing here different lines. In all of these cases, I am fixing the Z2 breaking scale at the 246 GeV, because in this case, for the 2HTM type 1 2HTM that we are studying, this would be roughly at this scale. It will not change much. On the other hand, the U1 breaking scale, it could be large. So for example, I'm looking at cases where it can be 10 to the power 12 GeV to all the way up to 10 to the power 15 GeV. And as you can see, as expected, higher scale for the U1 breaking leads to higher amplitude. And as you lower the scale for the U1 breaking, you have a slightly lower amplitude. That's the first thing to notice. The second thing is here, these dotted lines represent the corresponding gravitational wave for pure strings. So at the very high frequency, which corresponds to very early cosmic time, which is before the creation of the domain wall, you have the same kind of spectrum from the pure string and from the hybrid network. So it's essentially flat. And then, as you see here, although the pure string case would continue with somewhat flatter spectrum, but here, because of the creation of the domain walls, we see an somewhat early decay of the network. So in terms of gravitational waves, we see a fall off in the energy, which gives a distinct slope here. As you can see, for all of these different solid lines, the slope for the IR is given by f cubed, and this is a particular signature of this kind of topological defects. And this is very unlike the pure string case, in which case you have a slightly smaller slope. So this is one way of detecting whether the signal is from a pure string network or it is from a hybrid network like this. As I mentioned, doing this calculation for the pure string case is somewhat easier compared to in this case, essentially because of having to solve a numerical equation every time we sum up the modes. So we wrote this code package that will let you do this. Of course, it will also do the pure cosmic string case just by setting RC to be infinity. But you can use it to calculate different kinds of topological defects related to cosmic strings. Now, what are the major takeaways for this model? So one thing is, as I mentioned, that the infrared slope, it happens at somewhat higher frequencies compared to the pure string case. So by that, I mean, for example, for the red line, or let's say for the orange line. So this is starting to fall off at 10 to the power minus 3 hertz, whereas for the pure string case, it goes on and on up until like nanohertz range. And then we have this distinct slope of f cubed compared to a somewhat smaller slope for the pure string case. So that's the first signature. Then secondly, another interesting observation is that, for example, if we look at these dotted lines, which goes through the recently reported nanograph axis, we see that these would be unfavored by nanograph data. For example, this red line, it would be heavily unfavored by nanograph data because nanograph observes a slope which is much steeper than that. So one of the conclusion from the nanograph data is that it is not possible to have U1 symmetry breaking and related cosmic string, pure cosmic string, if the U1 symmetry breaking is as high as 10 to the power 15 GB, for example. Now that conclusion no longer holds for this kind of hybrid topological defects, because as you can see, because of the domain wall, we have the slope here, which falls off faster, and we are not even reaching the nanograph region. So we can still have U1 breaking at as high as 10 to the power 15 GeV, as long as there is an intermediate discrete symmetry, which creates a hybrid topological defect. So we are basically then making up room for some of the models. So if we have an intermediate breaking scale, it's no longer inconsistent with nanograph data. Then the third thing is that in a typical U1 symmetry breaking scale, you are looking at one symmetry breaking scale. However, in this case, we are simultaneously probing two symmetry breaking scales. One is the U1 symmetry breaking, and then the intermediate discrete symmetry breaking scale. So this gives us an interesting opportunity to look at BSM models where these two scales are separated by orders of magnitude. As I mentioned before, if they are too close to each other, then the effect of the domain wall happens much, much later. So the signal would be not too different from a pure string case. But if you have a big hierarchy between the two scales, in that case, you would see distinct effects happening as small as, for example, in the microhertz range to millihertz range. So in the visible sector where there are lots of interferometers planned, for example, LISA or even Einstein Telescope. So these would be able to probe this different kind of spectral slope compared to the pure string case. And finally, for this particular model, where the main prediction is that we have the Z2 breaking scale at roughly at the 100 GeV scale, or 246 GeV scale, but the U1 breaking scale can be large and unknown. So by looking at the flat part, we would get an idea of what the U1 breaking scale is. And then further, by looking at the F cube slope, depending on where that happens, we would get an idea about the ratio of the two symmetry breaking scales. So this particular model then can be probed beyond colliders into gravitational wave detectors if we observe this kind of F cube gravitational waves in the microhertz to millihertz range, for example. So this would be a unique way to probe this model from cosmological signatures. So to summarize, we were looking at a type 1 two-Higgs-doublet model extended by a gauged U1 symmetry, so which was initially motivated by, to incorporate the seesaw mechanism, it simultaneously cancels the chiral anomaly and eliminates the flavor-changing neutral currents. Then we saw that a particular U1 charge assignment that is required for anomaly cancellation, it leads to the U1 breaking via an intermediate Z2 symmetry breaking scale. And we have interesting cosmological implications for that the U1 breaking gives us a cosmic string network, but then the hybrid Z2 breaking creates domain walls, which gets attached to the cosmic string and gives us a hybrid walls bounded by strings kind of network. This is only possible when we have this kind of two-stage symmetry breaking chain. And then we studied the hybrid topological defects cosmological evolution, and we saw that the gravitational wave that is generated by this kind of defect is distinct from what we get in the pure string case. And in particular for this model, we saw that if the two symmetry breaking scales are orders of magnitude hierarchical, in that case, we can probe the implications of this model in upcoming telescopes in LISA or Einstein Telescope and other interferometers, particularly in the microhertz to millihertz range. I think that's what I wanted to talk about today. So if there are more questions, I'd be happy to take.
Thank you very much, Moinul, for the very nice talk. Question from the audience?
Yes, I have a question. Thanks, Mono, by the nice talk. I have two questions actually. First, these topological defects, the cosmic strings, they have to be always closed. This is because of the breaking of the two symmetry, or I mean in the case in which you have only strings, not domain walls, these strings could be open.
That's a nice question, actually. I didn't get into the details of it. So there are at least two models that people look at. What I described here is called the Nambu-Goto string model. So here you start with very long strings. So they're like linear strings, but then they kind of get tangled with each other. And wherever they intersect, we call that cusp. And there are energy emission from that cusp, so that then basically they get broken. So you have like two strings which are like intertwined at two places and they get separated, then it becomes like a loop. So this is one of the models, and these are all mostly coming from simulations, cosmological simulations. That's why there are there's another model called abelian Higgs model, which is slightly different. So in that case, we don't form loops, but it has different kind of predictions. So I think the Nambu-Goto string model is more popular in literature at this moment. Now, if you do not have intermediate Z2 breaking, what happens then? So you would still form these loops, and these loops would radiate energy, and they would shrunk, and eventually they would evaporate. And you would have gravitational wave signals similar to the lines, let me show here, similar to these dotted lines here.
Yeah.
What the domain wall network does is, so here, the relation between time and frequency is that higher frequencies correspond to what happens at earlier times. So at earlier times, the evolution of the hybrid network and the pure string network is very similar. But around here, when the domain walls are created and start to impact the evolution of the network, then these domain walls are like trying to make it, trying to shrink it further. So it's like an accelerated energy radiation from the cosmic string loops in terms of gravitational waves. And that's why we see that the energy is falling off quickly.
And that's because of the domain walls.
That's because of the dominance.
Because of domain walls. Okay. The second question is uh, 2 or 3 slides before this one. That is that theta function in the spectrum. This is an approximation because you are considering only the modes generated after this time t star. Is an
Yes.
approximation or
Yeah.
is physically required?
I think it's well motivated because you want to study the gravitational waves from the topological defect. So you want to zoom in on the relevant modes. So this helps us to only look at modes which are created after the domain was become important.
Okay. Okay, thank you.
Sure.
More question from the audience? Moinul had a question. In the plot that you show when you had several vacuum expectation value for the U1 prime symmetry breaking scale of 10 to the 15, 10 to the 13, and yes, this one. So it's in the, yes, for the highest value for the, for example, 10 to the 15, you could get maybe correlation between there will be some value for the some critical value for the frequency, in which you will overcome the experimental limit of LISA. I wondered if, for example, this could be maybe this highest, this high scale for U1 prime symmetry breaking can be related maybe with leptogenesis, because you will have type 1 realization of neutrino masses. So you may have also constraint from leptogenesis arising from the interference between 3-level and 1-level decay of the lightest of the right-handed neutrino. How you explored this connection with leptogenesis?
Yeah, so you're right. Essentially, when this symmetry breaking of the U1 would also give Majorana mass to the right-handed neutrinos. So roughly the masses, the Majorana masses sit at this scale. Then if you do vanilla leptogenesis, for example, from the decay of those right-handed neutrinos, then in that case, I think this would have impact on your leptogenesis calculation in terms of the masses of the right-handed neutrinos. So in that case, this amplitude of the gravitational wave would have a one-to-one correlation with the observed baryon symmetry.
I see. So in principle, this could also be explored, maybe to set limit on the mass scale of light-handed neutrino, or also to see under which condition baryon asymmetry parameter could be reproduced, and keeping this amplitude below the LISA, below the limit of the LISA experiment.
I'm sorry, what do you mean by below the limit of LISA?
Because this LISA, these are exclusion
Yes.
region, all these.
Oh, this is the region that LISA is supposed to probe. So if you
So it's still not. So it will be
yeah, it's
between
not
the
exclusion, sorry.
sensitivity. It's still
It's a
not
sensitivity. Right. It's a sensitivity, yes.
So it will
So
be
one of the sorry.
yes.
Now, I was saying that one of the reasons I didn't talk into this much is because, as you see, this is, the spectrum at this scale is very similar to the pure string case. So people have looked at the implication of leptogenesis in terms of gravitational waves, where you just have a U1 symmetry breaking that gives Majorana mass to the right-handed neutrinos. So the implication for that kind of model would be exactly same as this model here in the high frequency ranges, because all it requires is a U1 breaking. And in this range, it is not possible to probe whether there is an intermediate Z2 breaking or not. But people have looked at it. There is, I think, a paper from Hitoshi Murayama looking at how to probe high-scale leptogenesis or high-scale seesaw from gravitational waves.
I see. So for the strongest, yes, the other experiment, for example, the other plot that you show, these are, yes, I think these are the also sensitivity for the experiment, for example, the SIGO, MUARES.
Yeah,
These
these are all
also,
sensitivity except the LIGO, Virgo, and Kagra. So this is an upper bound. This
this is
LVK,
only upper bound.
this is an
So
upper bound.
always you are below the upper bound. There is no way to maybe be, I will say, very close to the upper bound, but below.
You can actually. So if you go to 10 to the power 15.5 GeV, then you are basically hitting this upper bound. And LIGO should have updated bounds soon. So I think it will be able to roll out even more. That's one of the reasons I stopped at 10 to the power 15 GeV.
I see.
And this
So this could
HLD, this is the expected sensitivity of the upgrade of LIGO. So, I mean, it's expected that LIGO would be able to rule out close to this soon.
So this could also put constraint on grand unified theories, because this
Yeah.
SU5, or for example, SU10 theories with like 100 neutrino, they will also have Taiwan seesaw higher scale Taiwan seesaw realization of neutrino masses. So maybe this model could be proof of collider, and maybe put some bound for this scale of the breaking of grand unified SU5 or SU10 or SU6 grand unified
Yeah, for
SU6
sure.
breaking.
Yes, for sure. Yes.
So maybe there is a way to also compare this model with the other GAT models, because they will fit maybe different gravitational wave prediction.
So there we have to be a bit careful, because this part of the gravitational wave spectrum, mathematically, it's only coming from a U1 breaking. It doesn't know about other phenomenology of the model. So let's say you have 10 models, all of them have U1 symmetry breaking at some scale, and then other things happen. All of those models would predict this kind of gravitational wave signal. So we have to be a bit
So it's a
careful.
generic pattern.
Sorry?
It's a genetic feature of models. There is no way to distinguish between different models.
I think we need to be careful. So this alone will not tell us that. We need other complementary information. This would just tell us that there is a U1 symmetry breaking happening at this scale. Now, there are many models where you could have a U1 symmetry breaking happening at that scale, but after that, what happens? Or what kind of particles you have? This has no knowledge of that. So we need complementary information.
I see. Thank you very much, Moinul.
Yep.
More questions from the audience?
Yeah, I have another question.
Yes.
The gravitational wave spectrum depend on other parameters other than the vacuum interpretation values. For instance, the Yukawa couplings to right-handed neutrinos, or not?
It would depend on the couplings also. So here I'm assuming roughly order 1 couplings, so that I can directly correlate the amplitude with the symmetry breaking scale. But of course, if your couplings are smaller, because in most cases, couplings multiplied by the wave, that is the parameter that enters into the equations.
So you assume order 1. If you put, for instance, 10 to the minus 2 or smaller, do you know what we could expect? What kind of
for
change in
example,
the spectrum?
Yeah, for example, here, this mu parameter, for example, so your overall gravitational wave amplitude is proportional to mu squared, right? Roughly, I mean, there are other places where mu enters, but roughly it's proportional to mu squared. Now, mu is roughly taken to be v square, where v is the symmetry breaking scale, and you have mu square, so it's like v4. Now, of course, there are here you have quartic couplings, which I have not shown. I have chosen them to be order 1. I think it's proportional to square root of lambda. So you have mu square, that means it will be proportional to lambda. That means if you have like order 2 suppression in the quartic coupling, then your gravitational wave amplitude will be suppressed by order 2.
But this dependence on the covers enters the equations via thermal corrections in the scalar potential, or not?
I'm not even looking at that. I'm just taking a tree-level potential without any correction, without any one-loop correction or thermal correction.
Okay. So it's
that would be further
this
computation.
scenario is quite different from first order phase transitions.
Yes.
Okay. I see.
Yes.
I see. Okay. Thank you.
Sure.
So you include thermal correlation, you expect that this correlation will not affect your result. Maybe this will be subleading. That's why you didn't consider, I suppose.
Yeah, it would be subleading. It would be subleading for sure.
It would be maybe 10% take correction, or maybe less than that.
I would say less, maybe 1%.
1%, huh? So very
1%.
very nice approximation neglecting this correction.
Yeah, yeah, yeah.
So in this case, there is no requirement that the phase transition be first order, anything of that. Just the formation of the domain walls is enough.
Yeah, yeah. In fact, if you have a U1 symmetry breaking where there is a first order phase transition, you can actually have two kinds of gravitational wave signals. One from the cosmic string signal related to U1 breaking, and the other from the first order phase transition.
Mm.
And we actually looked at it in a paper. Interestingly, if the U1 symmetry breaking is at sufficiently high scale, only then you would be able to see the cosmic string signal. Because as you saw here, the cosmic string signal is heavily dependent on the symmetry breaking scale. So if you are going, for example, down by 4 orders of magnitude, it's almost negligible. Now, if you have a first order phase transition at this kind of high scales, in that case, the first order phase transition signal will be suppressed first. Secondly, it would peak at a very high frequency. So there's I mean, if you see one of them and you can't see the other.
I see. At lower scales, you could see a first order phase transition. If the
Yes,
values
but
is-
in that case, there is also most likely a gravitational wave signal from cosmic strings, but they're so suppressed that people don't talk about it. Then you can make models where you can have both. So in that case, what you'd have is this flat part, and then there is this bump from the first order phase transition.
I see. Yeah, I'm thinking of seesaw models, neutrino mass models. So I'm thinking like type 1 seesaw model. It's better to look for gravitational waves from cosmic strings, topological defects. And radiative seesaw models in which the scale are in general much lower, you could look for first order phase transition because
Yeah,
the scale. Yeah, okay.
yeah, yeah.
Great, thanks.
Sure.
More questions from the audience? If there are no more questions, we thank Moinul for the very nice and very complete talk, and we meet at the next seminar. Thank you very much, Moinul, for the very nice talk.
Okay. Have a good day.
Thank you so much. Bye.
Bye bye.
Bye.